In this video, we're going to go through the code provided in the textbook to represent a graph. Now, a couple of important notes about the code. First of all, I have made significant changes to the code provided in the textbook, and I did so to simplify things. For example, the textbook code used the Q interface and stack interface and those implementing classes that we've written this semester that are from the textbook. And I think that just complicates things. So I switched that out to just use the Java, stack, and list classes and Q classes. Another thing is they had some additional interfaces. I kind of simplified that. I kind of changed some of the naming. And I also removed some of the methods that we're not covering. So some things about shortest paths and things like that. So just be aware that the code I'm going to show you and the code you can download from Canvas is a little bit different from the code in the textbook. You're welcome to look at the code from the textbook and add that back into these files and run those additional methods that have been removed. But I just modified things because I think that graphs can be tricky enough to get your head around, and so I think that it's easier to simplify them when possible, and I think that the textbook version of the code made things a little bit unnecessarily complex. So I just wanted to give you that heads up. So we have a couple classes we're going to look at. We have a class for edge, vertex, and then we have directed graph and undirected graph, and then we're going to actually create some graphs. So let's just start with the edge class. The edge, actually, let's start with the vertex class. We'll start there. So the vertex class, it's a generic class because our vertices can hold, strings or integers or student objects or whatever. And this particular implementation uses an adjacency list. So we have the data that represents our current vertex, and then we have a list of all of the edges of where this vertex is connected. So the edges originating from this vertex and going to some other vertex. We also have a variable visited that we can use for our various traversals and ordering. So in a lot of the traversals that we've looked at, the algorithm usually involves marking something as visited for many of the algorithms, and so we want a way to do that. So we have a variable to represent that. So for our constructor, we just initialize the data and create a new empty list. Now I've used a linked list. You could also use array list. You should think about kind of the differences and what might be the more efficient choice. We've just got some basic getters and setters. We have a way to visit a node, or a vertex rather, and again, that's to use when we're implementing some of our algorithms. We have a way to unvisit that vertex. We have a way to check and see if it's visited. And then we have the connect method. So this is really the way that we can build our graph by connecting vertices together. So the way you connect a vertex together is you would invoke the connect method on a vertex, and you would send in that ending vertex. So the current vertex is the beginning, the parameter vertex is the ending, and then you can also send in the weight. So what we do is we first check to make sure these are different vertices. Now, this means that you would not allow loops in this particular graph. Some graphs do have loops. A loop is an edge that connects a vertex to itself. This particular implementation doesn't allow that. If you wanted to allow that, you would have to modify the code a little bit. But right now, we're going to check to see, let's make sure that these vertices aren't the same. And if that's the case, what we do is we come in here and we get our neighbor iterator. We'll look at that method in a moment, but essentially this is just an iterator that's going to iterate over all the neighbors of the current vertex. And what we're doing is we're trying to see if the edge already exists. We want to avoid adding a duplicate edge. So we just go through that list of neighbors. We go through the neighbor iterator and say, as long as there's another neighbor to look at, let's take a look at that neighbor. And if that's the one that I'm trying to connect to, then I've found a duplicate edge and I can exit out of my loop. As long as I haven't found a duplicate edge, all I'm going to do is I'm going to create a new edge going from my current vertex to my ending vertex with whatever that weight is, and I'm going to add that new edge to my list and return true. If I failed somehow, if either I was trying to add a duplicate edge or I was trying to add an edge to the vertex itself, I'll just return false. So then, again, all this connect method does is it just makes sure that you are adding a new edge to a vertex other than the current vertex, and to do that, it just creates an edge object and puts it on the list. There's an overloaded connect method that doesn't take in a weight, so this would be for unweighted graphs, and what we do there is we just assume that the weight is 0. So otherwise, the process is the same. So let's briefly flip over now to the edge class. The edge class in the textbook is written as an inner class, and again, I changed that because I think it can be helpful to just see edge all on its own. The way we represent an edge is from it just has the ending vertex. So that can be a little bit confusing, and maybe that is the one part that is less confusing, having it be a nested inner class. But essentially in this representation, we're only ever adding an edge to a vertex's adjacency list. So that vertex is the beginning vertex. So we don't need to keep track of that. All we need to do is keep track of that ending vertex. So all we do is we just capture the ending vertex and the weight, and we have an overloaded constructor that doesn't take a weight, that just has a weight of 0, and then we just have some getters, and that's it. If we wanted to have an edge class represent both the beginning and the ending vertex, we could certainly do that. That would be an easy change to make. All we would do is when we were creating that edge, we would send in this, for the beginning vertex and then our ending vertex. So that's how we can connect vertices up. Now let's go down and look at that get neighbor iterator. So this is the method that's going to return to us an iterator that iterates over the vertices. So this is essentially a way to iterate over the adjacency list. However, our adjacency list holds edges, and we want to iterate over the neighbors, right? Like we don't care about the edge, we care about the vertex that edge connects us to. So that's why we can't just have an iterator over the edge list, because that would give us edges. So instead, we're going to create an iterator over the vertices. So to do that, there's a nested class called neighbor iterator. And all that does is it just creates an iterator of the edges. That's just a regular Java iterator, and it just iterates over that list. But instead of returning an edge, it says, okay, when we have the next edge, when the edge iterator has another element, all I do is I get that edge and I get the neighbor, and that's what I return. So this is just sort of a little encapsulated way of saying instead of iterating over the edges, I'm iterating over the neighbors or the vertices represented in that edge. So it looks a little complex, but it's actually a pretty simple idea. It's essentially just related to the fact that our list stores edges, and when we want to look at neighbors, we want to look at the vertices. So we need to kind of extract the vertices out of each one of those edges. There is similarly a weight iterator. So let's say we wanted to know the weight edges. So this would be used, for example, if you were looking for a shortest path between two vertices, or a cheapest path between two vertices, I should say. You might want to be able to sum up all the weights of a group of edges. So what we can do here is we can again extract those weights out of the edge list. So the iterator that goes over the edge list is just going to give me the edge, but all I care about is the weight. So what I'm going to do is I'm going to return the weight as a double. That's what I'm going to iterate over. Okay, so instead of iterating over the edge, I'm just going to essentially iterate over the weight part of that edge. So those are our iterators that are defined here. And again, we use that iterator in the connect method to make sure that that edge we're trying to create doesn't already exist. So that's our connect method. And we have a method to get the neighbor iterator. We have a method to see if this vertex has any neighbors. And all that does is it just returns whether the edge list is empty. There is a method to get an unvisited neighbor. So some of our algorithms ask for, I'm looking at a vertex, give me an unvisited neighbor. So we want to be able to do that. So we use the neighbor iterator again to say, give me an iterator that goes over all the vertices connected to this current vertex. And all I do is I say, okay, as long as there's more to look at and I haven't found an unvisited neighbor yet, I just get that next neighbor off the iterator. If it's not visited, then that's my result. If I get all the way through this loop, that means that either this current vertex doesn't have any neighbors or all of their neighbors have been visited. And in that case, I just return null. Okay, so this method here gets you some unvisited neighbor. Now, note that this method is not going to get you the unvisited neighbor in alphabetic order. I leave that to you to think about how you might make that happen. You would essentially have to define a way to order edges, and you'd have to sort that list according to that ordering so that the edges are returned to you in alphabetic order or whatever order you want to choose, like we've been doing in the videos. But this particular implementation isn't going to do that. Now that's okay, because remember, the order in which you visit a neighbor is not part of any of those algorithms. We use alphabetic order just for kind of consistency and simplicity in learning them, but that's not part of the algorithm. Any visitation order is fine. Okay, so that is our get unvisited neighbor method. And then we have an equals method that just compares whether the data is the same. And because we don't allow any duplicate, we're not going to allow any duplicate vertices in our graph, that's enough to compare. We don't have to compare edge lists because if we're not going to allow a graph with vertices that have the same data. So that is our vertex class. I added one more, or we have a method to get that weight iterator, and I added one additional method that's not in the textbook, and this is just a display method. And all this does, it just prints out the data and then an arrow, and then it just prints out a list of the neighbor vertices. So it prints out the data contained in the neighbor, as well as the weight of that edge. And if the weight is 0, I just don't print any weight at all. But if there is a weight, then I print that weight. So this is just kind of for testing purposes, this display. It can help us to visualize our graph. So that is our edge and our vertex classes. Now we have two classes to represent the actual graph, a directed graph and an undirected graph. There's also a graph interface, and really the purpose of this is just to sort of, capture up all of the functionality of a graph into one interface, and we can then implement that in both directed graph and undirected graph. This could also be an abstract class. I think if I was designing it, I would probably make it an abstract class, but that's not the inheritance structure used by the textbook, and I didn't want to make such a major change to change that. So they chose to make this an interface, and it does make sense as an interface. I think it could work either way. So the functionality you want for any graph is you want to be able to add a vertex to the graph. You want to be able to add an edge between vertices with this particular data, and you want to be able to have that edge have a weight. You also want to be able to have an edge that doesn't need a weight, so this would be for an unweighted graph. You want to be able to test if there's an edge between two vertices. You want to know if your graph is empty. You want to be able to get the number of vertices, get the number of edges, clear out the graph, and then you want to be able to traverse or get the order of the vertices in your graph. So you want to access a breadth first traversal, and that will return to you a queue of data, and you want to be able to get a depth first traversal, and that will also return to you a queue of data. Now, both of these methods take in an origin vertex, right? Because we know that our traversals depend on the origin from which they start. You can also get the topological order. That will return to you as a stack. And of course, there we don't take in an origin. That's not part of finding the order. And then I also just included display. Again, this is just kind of for our testing purposes. So I didn't comment it or anything. I just kind of slipped it in there. So let's first look at directed graph. So our directed graph class implements our graph interface, and we're going to implement the directed graph by using a map. So our map is going to take us from the data, so this is like the label, in our case we're just using letters, to the actual vertex itself. So this is just a way to say, okay, if I have A, the data A, give me the vertex A. Okay, so it's just a way to connect those two things. We could have changed this implementation another way by saying, instead of having all of these parameter types be T, we could have made them vertex. And then we'd have a little bit of a different implementation, and we wouldn't necessarily have to use a map. We could just use a list. But for us, the map allows it to be a little bit more efficient, and so that's why this implementation was chosen. The other variable we have is just an edge count. So when we create our directed graph, it's just initially empty, and we just say we have no edges. So we have to implement those methods in the interface. So the first step is adding a vertex. So to add a vertex, we want to put a new vertex in that vertices map. So to do that, we send in the data. So that's what comes in as a parameter. And then we create a new vertex by just passing along that data. And the put method of hash map will return either null, and that means that previously there was nothing in there. There was no entry in the map for that particular data. It used to be null. Now it's going to have our new vertex data. But if it used to be null, that means we successfully added. Okay. If there was already a vertex in there, the put method will replace it, but it will also return to us the old data that was in there, in our case, the old vertex. So if we get an old vertex coming back, if this return value is not null, that means there already was something there, and we've essentially replaced it, but we want to indicate in some way that, we didn't actually add a new vertex, we just replaced the data that was already there. So that's what this return statement indicates. So if this is a new vertex, this returns true. And if the vertex is already in the map, so already in the graph, this returns false. Okay. So the other method, the next method, we want to add an edge. So in order to add an edge, we have our beginning vertex or our beginning value and our ending value, and then we have the weight. So remember that with our graph, we're just using data, but behind the scenes, we need the vertex for that data. So the way we do that is we just use the get method in our map, and we ask for the vertex that has that particular beginning data. We ask for the vertex that has that particular ending data. That'll give us back two vertex objects. We check to make sure they're not null. So these would be null if they didn't exist in the graph. So if our graph has A, B, C, D vertices and someone tries to add an edge from B to E, E is going to be null, and so we don't want to add that edge, and so this will fail. So here we just make sure they're both not null, and then we just invoke that connect method, connecting from the beginning vertex to the end vertex with this particular weight. Assuming that result is true, so remember the Booleans returned from that method is just making sure that we're not trying to connect a vertex to itself, and we're not trying to add a duplicate edge. So assuming this returns true, that will update this to true. So if this conditional fails or if the connect method fails, then I'll return false. If neither of those happens and I successfully add my edge, then I return true, and I also update my edge count. There's an overloaded add edge method that just again allows me to add an edge with no weight, and there I just invoke this method here, passing along a weight of 0. To determine if there is an edge between two vertices, I start the same way. I need to get that vertex object out of the map, make sure it's not null. Of course, if either one of those is null, then that edge can't exist because the vertex doesn't exist. But assuming that's not the case, assuming someone gives me two vertices that are actually in my graph, what I do is I just take that beginning vertex and I just get the neighbor iterator. Remember that neighbor iterator is an iterator that allows us to look through all the neighbors of my beginning vertex. So I say, well, as long as I haven't found this neighbor, and as long as I have another neighbor to look at, let me get that neighbor off the iterator. And if that's the one I'm looking for, then hey, I found it. If I get all the way through this loop and I haven't found it, then that means that there is no edge between those two vertices. To know if a graph is empty, we just check and see if the map is empty. To clear it out, we just clear out the map and reset our edge count. To get the number of vertices, we just return the size of the map. Get the number of edges, we return the edge count. To reset the vertices, so this is a way to kind of unvisit all the vertices in our graph. So remember that for a lot of our algorithms, we need to visit certain vertices. When that algorithm is done, we'd want to unvisit everything, kind of reset it. So what this does is this just gets an iterator over all the vertices in the graph, and I do that by getting the values of the map and getting an iterator for those values, and then I just go through and I unvisit all of those vertices. So this invokes the unvisit method from the vertex class. The rest of our graph our graph class, directed graph class, is the methods for getting breadth first traversal, depth first traversal, and topological order. I'm going to come back to those in a moment, but first I want to use our tester to invoke the methods that we just looked at. And then I also did add a display. This is again just for our kind of printing testing purposes. Our graph will tell us how many vertices it has. Our display method rather will tell us the number of vertices, the number of edges, and then it will just get an iterator of all of the values and iterate all the vertices rather by getting the values from the map, and it'll just iterate over and display each one of those vertices. So let's go into our graph tester, and we're going to actually create some graphs. So to do that, I'm going to start by creating a directed graph that just holds strings, and I have a method that I'm going to use to do that. So I'm going to create the graph that was on slide 11. So that is this graph here. This is my directed graph. You can see it has 1, 2, 3, 4, 5, 6, 7 vertices and a bunch of directed edges. And it's unweighted. This is the graph I'm going to create. So down in my tester program, here is what this is the code that I'm going to use to build my graph. So for each one of my vertices, I have the code to add a vertex. So you can see I'm adding the vertex G, H, J, N, M, K, and P. And then I just go ahead and add all those directed and unweighted edges. So I add an edge from G to N, G to H to N, J to H, J to K, M to N to H, N to K, N to P, and N to M. Okay, so that's how I build my graph. Now, one thing to note about using graphs is that we usually use graphs for different things than trees. A lot of times with our trees, we're building trees and then we're adding to trees and we're looking for elements inside of a tree, seeing if a tree contains an element. a lot of times graphs are used in a different way. A lot of times we don't continue to add things to a graph, but we sort of build the whole graph at once. And then we're often more interested in the relationships of the vertices in that graph. So who's connected to who, what is the path between one vertex and another? What are the weights of those paths? So it's not very common, or I should say it's less common that we're kind of building a graph and then adding to it and removing from it. In fact, right now there isn't even a way to remove from it, but that's not as common. That is common with trees, right? We build a tree and then we add to it. We saw a lot of examples of that. But with a graph, that's not a lot of times what we want to do. A lot of times instead we just want to build this graph, and that graph represents some data set that we're looking at. And what we want to use that graph for is exploring that data set, looking at the relationship between those vertices. So to do that, that's when we're going to use our breadth first traversal, our depth first traversal, our ordering, or also some of those algorithms we're not talking about that I encourage you to look at on your own about, shortest path and cheapest path and things like that. So that's kind of a difference in how the code looks, because it's a different purpose that we're building this structure for. We're building it to really kind of examine it rather than to continually add to it. Okay, so there is our building of our unweighted graph, directed graphs, our unweighted digraph. Okay, so let's now finish up looking at the methods in the class. So there are our two traversals and our ordering method. Now this code just follows the pseudocode that we looked at in the slides. So we take in an origin for breadth first traversal. We have a queue for our traversal order and a queue for our vertex queue. We get our origin, we mark it as visited, and we put it on the traversal order. We also put it on the vertex queue. As long as that vertex queue is not empty, has something in it, we take the vertex off. We get all of the neighbors of that vertex. For all of those neighbors, if they're not visited, we visit them, put them on the traversal order, and put them on the vertex queue. And we go through that whole loop. Then we loop back up around, take another vertex off the vertex queue, get its neighbors, put any unvisited neighbors into the order and onto the queue, and we continue on. So this code here just exactly follows along the algorithm that we traced. Same thing for depth first traversal. Okay, so here we have a queue for our traversal order, and remember, for depth first traversal we use a stack. So we start out by getting the origin, we mark it as visited, we put it in the traversal order, and we push it onto the stack. Then as long as that stack isn't empty, we peek, get all the unvisited neighbors, so that's where that get unvisited neighbor method comes in. We get some unvisited neighbor, so that's where that get unvisited neighbor method comes in. And again, note that in this implementation, it's not going to be the alphabetic next neighbor. It's just going to be some unvisited neighbor, and that's okay. As long as that neighbor isn't null, so as long as there is an unvisited neighbor, we visit it, put it in the order, push it on the stack. If there are no unvisited neighbors, we just pop that element off the stack and cycle back around. So again, this is the same algorithm that we traced through, just now written in code. Same thing for the topological order. So for the topological order, the first thing we're going to look at is there's a helper method we're going to use called find terminal. And what this does is it's finding a vertex that meets those qualifications that we had for looking through our vertices in topological order. Remember, we need to look at a vertex that is unvisited and either has no neighbors or only has neighbors that have been visited. Okay, so it either has no neighbors at all or it has neighbors that have already been visited. And that is the characteristic we're looking at. So this algorithm is the first one we looked at, the one that looks at visited neighbors, not the in degree one. I leave that up to you if you want to play around with implementing that second implementation approach of topological order. But for this one, what we're doing is we're looking for always that vertex that is both unvisited and has only visited neighbors. So meaning it either has no neighbors or all of its neighbors have already been visited. Okay, so to do that, what we can do is we can just get all of the vertices in our graph. So we get the values from the map and get an iterator for that. And then we just look through, as long as I haven't found one yet, found some vertex that meets my criteria, and as long as I have another vertex to look at, I get that vertex. I first make sure it's not visited. That's my first criteria that it has to match. And then I also say, okay, well, give me one of its unvisited neighbors. If it doesn't have any, then hey, I have found my match, because either it doesn't have any neighbors or it doesn't have any unvisited neighbors, so meaning all of its neighbors have already been visited. And so this meets my criteria. So I'm going to mark that I've found one. I'm going to set that to be my result. And at the end, I will just return that result. If I'm all done, if there are no longer any neighbor or any vertices that meet my criteria, I'll just return null. So this is the method, again, that finds that neighbor that meets our criteria. And again, here, it's not going to be in alphabetic order, but that isn't part of the topological order algorithm. So going back up to my get topological order, all I'm going to do is I'm going to reset everything, which I believe actually that's also, I neglected to say that's the first line in the other two traversals as well, is resetting everything, marking all of those neighbors as unvisited again. I would probably, for safety's sake, put that at the end of each method too, but they don't have that here. Anyhow, so we reset all the vertices, we create our vertex stack, and then we figure out how many vertices we have, because we know that a topological order will contain all vertices, even if our graph is disconnected. So we know that all of those vertices have to end up in our graph, in our stack, and then we just have a loop. We go through the number of times, we find a vertex that meets our criteria, we mark it as visited, we push it on the stack. Find the next vertex that meets our criteria, mark it as visited, push it on the stack, and then we return that stack. Okay, so that is our directed graph class. Now, the last class we have is undirected graph, and the way they structured this is they used inheritance, so that they said an undirected graph extends from directed graph, so it basically gets all of that code from directed graph, and all we need to do is change very minor things. Essentially, we just want to, when we add an edge, we're basically adding two edges, right? So if we are adding in an undirected graph, if we're adding an edge from A to B, then by default, we're also adding an edge from B to A, right? Because the edge goes in both directions. So all we have to do is invoke the directed graph version of adding an edge twice. That's all we have to do to make it an undirected graph. And similar with the overloaded method here, we just are going to refer back to that directed graph version. The other things we need to change is the number of edges. We divide by 2 because you don't count an undirected edge as 2 edges. You just count it as a single edge. And then the other thing we override is the get topological order. Topological order does not make sense for an undirected graph. So if someone tries to invoke that on an undirected graph, we just throw an exception saying, hey, you can't do that. So that's our undirected graph class. So going into our graph tester, I showed you that we created a directed graph. I've also created a directed graph an undirected graph. And that is for the one on slide 10. So I also create this graph here. So again, I just have a helper method to do that, to build my weighted, this one is weighted, and undirected graph. Come back. Okay, so here you can see I'm adding vertex G, H, J, K, M, and N, and I add an edge from G to H with weight of 3. Now, I don't have to add it from H to G, right, because the implementation does that for me. It just says, yeah, well, if there's an edge from G to H, there's also an edge from H to G, so it does that behind the scenes. I add the edge from G to K with a weight of 2, G to N with a weight of 2, H to J with a weight of 4, J to K with a weight of 6, K to M with a weight of 4, and M to N with a weight of 5. So I've now built this graph as well. So let's go back up to the rest of our tester program, and now you can see I've built these two graphs, and I put them in a list just because I want to do the same things with both of them. So for each one of these graphs, first with the unweighted directed graph and then with the weighted undirected graph, I just want to display the graph, and then I want to look at the breadth first traversal starting at 2 particular origins, and then the depth first traversal starting at 2 particular origins. So let's print this out. Run this, I should say, and look at the output. So we start with our unweighted directed graph. That's this one here. And here is the adjacency list. So we can say 7 vertices. That's true. 10 edges. 1, 2, 3, 4, because this is 2 edges. 5, 6, 7, 8, 9, 10. So that's right. And then here we have our adjacency list. P doesn't have any neighbors. G has a neighbor of N and H. H has the neighbor of just N, J has a neighbor of H and K, and so on. So there is our adjacency list. I also have my breadth first and depth first traversals. So my breadth first traversal, if I start at G, I'm first going to visit H and N because they're one step away from G. Now note that again, this is the reverse order than we did it in the previous slide, but that's still a correct breadth first traversal. Next up is going to come K, and M and P, because those are 3 steps, or those are 2 steps away from G. So that's my breadth first traversal. J is not included because there's no way to get to J from G. My breadth first traversal of K is just K because K doesn't have any neighbors. My depth first, starting at M, goes M, and then we follow down as far as we can. So we have M to N to H, and then we're done. So we back up one level to N, and then we go down to K, and then we're done. So we back up one level to N, and then we go down to P. Again, the order of those is going to be different from the one we traced, but that's okay. My depth first, starting at J, is going to go J to H. It's done. So I back up to J, J to, oh, sorry, it's not done. J to H, H to N, N to K, I'm done. So I back up one to N. I then go down to M, back up one to N, then go down to P, back up one to N, back up one to H. That's done, and I'm done. Okay, so there is my breadth first and depth first traversals. Looking at our undirected graph, here is the printout for that. And again, we have 6 vertices and 7 edges. 1, 2, 3, 4, 5, 6, 7. 7 undirected edges, that's right. And here you can see my adjacency list with the weights associated. So G has an edge from H to N with the weights of 3 and 2, and an edge to K with a weight of 2. H has an edge from H to G with a weight of 3, and H to J with a weight of 4, and so on. My breadth first, starting at G, is going to first visit H, K, and N, because those are all G's direct neighbors. And then after that, it will visit J and M, because those are one step away. I go G to H to J, and G to N to M. And that's my breadth first, starting at G. Again, order of the visitated nodes are going to be different. Visited nodes, that's okay. That's not part of the algorithm. Breadth first, starting at K, I'll first visit J, G, and M because those are all direct neighbors. And then I visit H and N because those are 2 steps or 1 step away, 2 vertices away. Depth first, starting at M, I go M to K to G to H to J, and then I am done as far down as I can go. So I back up to H, still done, back up to G, still done. Then I go over to N, then I back up to G, back up to K, back up to M, and I'm done. Depth first, starting at J, I go to J, to H, to G, to K, to M, to N. And then when I back up, I'm actually all the way done. So there are examples of my breadth first and depth first. Now, I have some commented out code here that allows you to get the topological order. So first it checks to make sure that the graph you're looking at is a directed graph, because of course we know that we can't have topological order of an undirected graph. So first it checks to make sure, and then if it is, it prints the topological order. However, we can't run this on the graph that we're using here because this is not acyclic, right? You cannot have a topological order of this. Think for a moment of why. So the cycle is actually the 2-sided edges, M to N and N to M. We can't have a topological order because according to this graph, N would have to come before M and M would have to come before N, and that's not possible. So I can't have a topological order of this graph because it has a cycle. So that's why I commented this out, but I did leave the code in here because if you want to create your own graph and you want to build it and you know that make it a directed acyclic graph, I just wanted you to see how you can then get the topological order. I also leave it up to you as an exercise if you'd like to write a method to check to see if a directed graph is acyclic, and then you could invoke that first. You could say, well, if the graph is a digraph and it's acyclic, then I'm going to go ahead and get the topological order. If you had both those checks in there, you could just leave this code uncommented all the time. So I leave that up to you as an exercise as well. So there is an overview of the graph code with a couple of graphs created. I encourage you to create some more graphs, trace through those traversals using the code and using the slides, and make sure you kind of have a good sense of both the kind of logical idea of a graph as well as the behind the scenes implementation.